Hello everyone, thank you for coming. I will introduce the hardware-related content of the RTL87X3E series to you. I will introduce 5 aspects: hardware, application circuit, layout guidelines, reference design, and QVL of key components. The first part is an introduction to hardware design. Firstly, the 87X3E series includes 5 package types: QFN40, QFN50, AQFN76, QFN68, and BGA149. The QFN40 package size is 6 mm by 4 mm, with models including 8763 EFL. The QFN50 package size is 6 mm by 4 mm, with models such as 8763 ESE, 8763 EAU, and 8773 ESL. The AQFN76 package size is 8 mm by 6 mm, with models including 8763 EWM and 8763 EWS. The QFN68 package size is 7 mm by 7 mm, with models like 8763 EWE and 8763 EWE-VP. The BGA149 package size is 7 mm by 7 mm and corresponds to the model 8763 EW. Here are the pin layouts corresponding to different models. Among them, the pin layouts for the 8763 ESE and 8763 EAU models are identical, and the pin layouts for the 8763 EWM and 8763 EWS models are identical as well. The difference between the 8763 EWE and 8763 EWE-VP is that the VP version has built-in PSRAM. The 8763 EW uses a BGA package. The internal block diagram of the chip includes several components such as the CPU, DSP, memory modules, RF module, audio module, power module, and various peripherals. In the audio section, there are 2 ADCs and 2 DACs, which externally connect to SPK, mic, and aux. The power section includes LDO33, 1.8V for the codec, 1.2V for digital/RF, LDO AUX, MIC-BIAS, and a 3.3V supply for the RF module. The peripherals include interfaces such as SPI, I2C, UART, LED, AUX ADC, and PWM. Additionally, the chip features USB 2.0 and SWD, where SWD is used for debugging purposes. The chip is powered by VBAT, which is the main power supply pin for the entire IC. The supply voltage range for VBAT is from 2.8 volts to 4.5 volts, making it suitable for Li-ion battery applications. The 87X3E chip supports displaying battery level in a customer app. To implement this feature, customers need to first create a battery discharge curve. It's recommended to fully charge the battery, then discharge it using a 5 to 10 mA load from 4.2 volts to 3 volts. During the discharge process, divide the time into 10 equal segments and record the corresponding voltage values. These values are then entered into the MCU config tool, with each voltage corresponding to a percentage. Once configured, the headphone's battery level can be read by the phone while the headphones are in use. The 87X3E chip integrates a charge module that supports Li-ion battery charging through the ADP-IN. The operating voltage range for ADP-IN is 4.5 volts to 5.5 volts. For models that do not support one wire, the ADP-IN voltage can reach up to 6.5 volts. The maximum charging current is up to 300 milliamperes, and the battery level can be read via at commands. The charging process is divided into 3 stages. When the battery voltage is below 3 volts, charging occurs in trickle mode. In this mode, the current is fixed at a set value, such as 0.1 C, which can be configured in the tool. Once the voltage exceeds 3 volts, the chip enters CC mode, where the charging current can be set to 1 C. When the battery voltage reaches 4.2 volts, the chip switches to CV mode. In CV mode, the voltage is maintained while the charging current gradually decreases. Charging stops once the current falls below a predetermined value, which can also be configured in the tool. Additionally, a recharge voltage can be set, triggering a recharge cycle if the battery voltage drops to this level. The charging module also supports ambient temperature detection. Charging will stop when the ambient temperature reaches a preset error value, and the charging current will be halved when it reaches a preset warning value. These values are configured in the MCU config tool. Temperature detection is realized through internal ADC sampling, with an external NTC and a resistive divider connected to the ADC pin. Since the LDO-AUX power supply remains on during DLPS, this divider circuit will consume power. To reduce power consumption, a 5-volt signal can be used to control a MOSFET, turning it off when not charging, thus achieving power saving. This will be discussed in the application section later. Additionally, the voltage for the ADC should not exceed 0.9 volts. Recommendations and calculation methods for the resistor values in the NTC divider are available in the SDK, which can be referred to for guidance. The chip integrates 2 switch-mode power supplies internally, converting the VBAT voltage to 1.2 volts and 1.8 volts, which supply power to the CPU and audio sections, respectively. The 2.2 microhenries inductor and 4.7 microfarads capacitor must be designed according to a reference circuit, and their values must not be changed. The models for the inductor and capacitor can be selected from the QVL. The HWRSTN pin is active low and has an internal 100K pull-up resistor. To prevent interference from other signals, a 0.1 microfarads capacitor should be connected externally to this pin. If HWRSTN is held low for more than 8 milliseconds, the system will reset. The 87X3E requires an external 40 MHz crystal, which serves as the clock source for the CPU and Bluetooth to operate properly. The crystal must be selected according to the models listed in the QVL. The load capacitance should be 7 picofarads or 9 picofarads. External capacitors are not required because the chip supports internal load capacitance selection, which is adjustable. Moreover, during mass production, it is necessary to adjust the internal capacitance to ensure the crystal frequency offset meets the specifications. A large frequency offset may lead to Bluetooth disconnection. The audio module supports analog output format with Class D differential output. The SNR can reach 106 dBA with a 32 ohms load and 104 dBA with a 16 ohms load. The noise floor is at -106 dBA. The analog output can be connected to a speaker and only supports Class D differential mode. If you are connecting to a speaker, use the differential output directly. For speakers that require higher power, a power amplifier should be added before connecting to the speaker. Additionally, LC filtering should be applied to the Class D output. The audio input section supports AUX-IN, 3 analog mic inputs, and 4 digital mic inputs. The analog mic inputs offer dual microphone echo noise cancellation and neural network algorithms. The A-mic SNR can reach 96 dBA, and the AUX and SNR can reach 95 dBA. The system resolution is 24-bit with a sampling rate of 96 kHz. The RF section supports dual-mode Bluetooth output. The maximum output power of BDR is up to 10 dBm, and the maximum output power of EDR is up to 7.5 dBm. The RX sensitivity at 2 mega EDR is -94 dBm. To achieve good RF performance and harmonic suppression at 10 dBm, it is necessary to add a matching network to filter out higher-order harmonics. The values of the matching network components should not be changed and should be selected based on the QVL. The layout design should reference the layout guide to ensure optimal performance. For the antenna selection, you can choose from options like PCB antennas, ceramic antennas, or pogo pin antennas. When using a PCB antenna, it requires a complete clearance area to ensure optimal radiation characteristics. If the clearance area is not maintained, the radiation properties may be affected, and the center frequency could shift. It's important to avoid placing metal components, batteries, speakers, or similar objects in the direction of the antenna's radiation to prevent obstruction of the RF signal. When opting for a ceramic antenna, it tends to be smaller in size compared to PCB antennas, and its performance is generally more stable. However, the design should strictly follow the manufacturer's guidelines for the ceramic antenna. Some reputable manufacturers are listed in the SDK for reference. For pogo pin antennas, the major advantage is that the antenna is mounted on the enclosure, slightly distanced from the PCB. During the design process, ensure that the antenna is placed more than 1 centimeter away from the PCB to avoid affecting the antenna characteristics. When tuning antennas, it is recommended to conduct testing using the complete usage scenario. Perform tests with the entire unit to account for the effects of the enclosure, battery, speaker, etc., as testing with a bare board might yield inaccurate characteristics. Additionally, it's advisable to test with a dummy head, as human presence can also impact antenna performance. Furthermore, the antenna should undergo efficiency testing in a lab to verify if the antenna design meets the original design requirements. If headphones are used in pairs, the antenna design for the left and right ears must be symmetrical. The antenna direction of the secondary earphone should be the mirror image of the main earphone. The direction of the maximum gain of the antenna should ideally be away from the head, as the human body absorbs some electromagnetic waves. This is a summary comparing different models of ICs. They have the same Bluetooth certification version, different packaging sizes, and different numbers of GPIOs. The codecs all have Class D outputs with the same output capability. Some support 3 channels of analog mic, while others support 2 channels. All models have the same 2 channels for SPK. Some models do not support USB and 1 wire. The maximum capabilities for RF-TX and RX are the same across all models. For specific details, please refer to the datasheet. The second part is an introduction to application circuits. Analog MEMS connection to RTL87X6E is shown in the following circuit. It is suggested to use the MEMS mic in difference mode, even though it outputs a single-ended signal. Since the MEMS mic lacks a mic end signal, connect the mic end pin of the chip to a nearby ground on the mic side. This setup helps to cancel out potential interference from the surroundings on the mic P line through mutual cancellation with the mic N. Place a 0.1 microfarad decoupling capacitor near the mic for the MIC-bias to reduce noise influence on the power line. Mic 1 for talk mic, and mic 2 for FF-ANC, or mic 2/3 for hybrid ANC application. D-Mic supports most of the industrial digital microphone in PDM format and is able to latch data at both rising and falling edges. The mic select pin controls whether the signal is active high or active low. Connecting the select pin to GND makes it active low, while connecting it to AVCC makes it active high. This configuration allows the output of two D mics to be read using a single D mic signal line. The audio also supports the aux-in function. The aux-in's left and right channels are connected to the audio interfaces left and right respectively. A GPIO is reserved to detect the insertion of an aux-in plug. When the aux-in is not plugged in, the switch is closed, connecting the GPIO to VDD, and the chip receives a high-level signal. When the aux-in is inserted, the switch opens, and the GPIO is pulled down to GND through a resistor, making the chip receive a low-level signal. The chip uses this mechanism to determine whether the aux-in is connected. RTL87X3E support up to 24 filter for hybrid ANC. Use 2 amms mic, mic 2 and mic 3 for FF and FB mic. Mic 1 for talk mic only. About the mic spec, we have some define as ANC design application note. Regarding the application of I2S, it supports both master mode and slave mode. In the master mode, BCK is provided by configuring GPIO and it does not support MCLK output. BCK is a jittered clock composed by two frequencies that generated from 40 MHz. Slave needs to be evaluated the tolerance of BCK accuracy. In the slave mode, BCK/LRCK come from master via GPIOs and support de-jitter. In this case, the 8773 ESL is used as a slave. The 8773 ESL receives BCK and LRCK signals from the master, outputs data via SDO, and receives data through SDI. The fixed format for both TX and RX is normal I2S2 channel. The resolution is 24 bits and the sampling frequency is 48 kHz. The signals received by SDI require a maximum VIL of 0.4 volts and a minimum VIH of 0.7 VDDIO. Regarding the application of the ADC, it has an internal 12-bit SAR ADC with a total of 4 channels, and the input range for the ADC is 0 to 0.9 volts. One application is battery temperature detection. In this setup, the battery temperature is measured using an NTC thermistor and a resistor voltage divider to produce a voltage. It is important to ensure that this voltage does not exceed 0.9 volts, as it may damage the internal ADC. If power consumption is a concern, a MOSFET can be added in series with the voltage divider circuit. When not charging, the MOSFET remains off to reduce power consumption. One application of light sensor is in-ear detection. Taking HX3001 as an example, it is implemented by configuring GPIO through the MCU config tool, selecting the sensor's output and input signals. It is important to note that the sensor requires a 3 volts power supply, so the corresponding I/O should also be at the same voltage level. In the diagram, P10 and P1-1 are connected to the sensor. P10 is connected to the LD-, controlling whether the internal laser is operational to save power consumption, and P1-1 is connected to Vout for receiving data. The third part is layout guidelines. For the power section, the capacitor for the HV pin should be placed close to the IC, and its placement is the top priority. HV serves as the input for both the core and audio buck circuits. If the HV capacitor is placed far away, it may result in large voltage transients at the input of the buck circuit, potentially damaging the internal switching power supply. Another chip, the JSA1227, can be implemented by configuring I2C and INT in the MCU config tool. RTL87X3E supports the special calibration flow when in mass production flow. Please contact software team if you would like to choose this sensor. Next, the output inductor and capacitor of the buck circuit should also be placed close to the IC. If placed too far away, it may result in significant ripple on the 1.2 volts line, affecting the performance of RF and audio. The trace width is recommended to be 20 mm. Keep the loop area as small as possible. Avoid routing traces in the area directly beneath the inductor. Thirdly, the capacitor for VBAT should also be placed near the chip. The trace routed must go to the capacitor first, and then go into the input of chip. The trace width suggested to be 15 mm at least. The RF trace needs to have a 50 ohms impedance match, and components should be placed in a straight line as close together as possible, with no additional traces to prevent the introduction of extra capacitance and inductance that could adversely affect the matching circuit's performance. Vias should be placed on both sides to reduce interference from external signals. A complete reference ground plane should be present beneath the RF trace to ensure a smooth return path, otherwise, it could lead to reduced RF power. The crystal should be placed close to the IC, with the trace width more than 6 mm. It is recommended to have a complete ground plane beneath the crystal to ensure a smooth return path and reduce EMI interference. For differential signals such as speaker P speaker N and mic P mic N, the routing should be done in differential pairs with a trace width more than 8 mm. It is important to note that auxin is not a differential signal, so it should not be routed as a differential pair. It is necessary to add enough GND via in the EPAD and connect with GND layer. The fourth part is the reference design. Here are the reference designs for two ICs. Each IC has its own corresponding reference schematic available for consultation, which is typically included in the HDK. The fifth part is key parts and QVL. This is a specification table for a 40 MHz crystal oscillator. Here are the key specifications. Load capacitance, 7 or 9 picofarads. Frequency tolerance less than or equal to plus or minus 10 parts per million. Frequency stability less than or equal to plus or minus 10 parts per million. Maximum drive level 300 microwatts. Equivalent series resistance for CL equals 7 picofarads. Maximum ESR equals 50 ohms for CL equals 9 picofarads. Maximum ESR equals 40 ohms. Minimum insulation resistance, 500 mOhms. The 40 MHz crystal oscillator has several models listed in the QVL that have been verified as suitable choices. For the 32 kHz crystal oscillator with a load capacitance requirement of 7 picofarads and an accuracy of plus or minus 20 ppm, there are two models available from Seward and Epson. For the switching power supply, it is recommended to use a wire wound power inductor. The inductance value should be 2.2 microhenries plus or minus 20%, with a self-resonant frequency greater than 40 MHz. The DCR should be less than 1 ohm, better if 0.5 ohm is available, and the saturation current should be greater than 0.5 A, saturation current, max current while inductance decrease 20%. A QVL of suitable inductors is provided, which you can choose from. Check the inductor's saturation current instead of the rated current, as the saturation current is not the same as the rated current. The saturation current should exceed 500 milliamperes. Choosing this ensures that under high current, the inductance value meets the requirements, and the ripple is relatively small, which will ensure that the RF and audio characteristics are not affected. If the inductor's specifications only mention the rated current, it is recommended not to use it. Regarding the RF matching network mentioned earlier, the values of the matching network should not be changed. In the QVL, there are two series of ACX inductors to choose from, and it's preferable not to change the model. Regarding antennas, some manufacturers are recommended in the QVL. They can provide complete antenna solutions, and it is advisable to choose the manufacturers listed in SDK. For flash, we have tested several models, which are summarized in the QVL for your selection. Thank you for watching our presentation on the hardware-related content of the RTL87X3E series. If you have any questions, please feel free to contact us. Thank you everyone.